I posed a question on DSP forum relative to the use of real-only data paths for OFDM communication systems. On this slide, I show the traditional OFDM digital system where on the left side we start with a bit stream. The bit stream is converted to AB values. AB is in fact a grid point in what we call a constellation. The constellation that I showed there is a 4x4 grid pattern or 16 QAM. So we generate the AB, we generate one value of a complex AB and put that in a vector of length n, where n is the number of subcarriers used for our FFT and our IFFT. So you see the vector of AB points going into the IFT there on the left with a subcarrier length of n. Because we have n terms in the number of subcarriers and we have n terms in the AB input vector, that leads to a real and an imaginary output of the IFFT. We show there as they are called the in phase and the quadrature outputs of the IFT. Those then go into a rather universal device called an IQMixer. What the IQMixer does, it takes the two IQ signals and upconverts them using a carrier frequency. Carrier frequency must be much higher than the bandwidth associated with the real and imaginary input vectors. The outputs of the IQMixer are summed and then transmitted across a channel where we may have a disturbance of some kind introduced by the channel. At the receiver, we invert the process. The IQMixer takes the single input, again uses the same carrier as we used in the transmitter, and we produce an output that is approximately a mimic of the original I and Q values. However, because of the nonlinear nature of the IQMixer, we have introduced some extra terms that are far out in frequency, and in fact they are twice the frequency of the carrier. So we have to put these signals through a low-pass filter to filter out those higher frequencies, and we have to do that twice because we have an I and a Q channel. Once we have the I and Q channels, and these are sampled at the same sample rate and synchronization in time as we had back at the transmitter, these are input to an FFT, again of the length n, which then reproduces the A and B values and allows us to reintroduce the bit stream. So this completes the normal configuration associated with OFDM digital systems. As an example, we can do things very quickly, send a lot of data across a very compact bandwidth. The theoretical database for the above system sends 4 bits per modulation cycle, and remember, this is what I described in the upper part of the slide is a single modulation cycle, and these modulation cycles occur one after the other as time moves forward. So in a single modulation cycle, we can send 4 bits from the 16 QAM. We put each of those 4 bits can go on to one of the subcarriers of length n, which here we're going to assume is 64. And then we have to divide by the modulation time to get the actual data rate. For 802.11 with 64 subcarriers, 16 QAM, and a 20 hertz bandwidth without any forward error correction, we have a modulation cycle time of 3.2 microseconds. Multiply these numbers out, this simple system can give us 80 megabit per second. And we're going to modify this in a manner that we show here. Instead of using the IQMixer to send an I and a Q from the IFFT at the transmitter, we're now going to send real data from the IFFT. So what that means is that we have to have at least 2 times n length of the FFT vector that goes into the IFFT. And what happens here is that the AB vector, the complex vector that goes into the IFFT, has now length 2n instead of n. Well, we have to manufacture an extra n elements of the complex vector. And how do we do that? Well, we do that by reversing the order of the original n and using the complex conjugate. And once we do that, the output of the IFT will in fact be a real quantity, a list of real quantities, as opposed to a list of complex quantities. What that means is we can send in 2 bit streams. Each of those bit streams, after passing through the IFFT, will be real. Now we use the same IQMixer as before, but instead of sending in real and imaginary terms, we send in 2 separate sets of real terms from 2 separate bit streams. These are summed as before out of the mixer. They go into the channel, and the exact opposite happens at the receiver. Everything goes into the IQMixer just as before. Out of the IQMixer, we have the extra high frequency terms at twice the carrier. Run those signals through 2 separate low pass filters. Now we have 2 separate FFTs, and we can recreate the separate A and B vectors for each of the separate bit streams. And we in fact have twice the data rate that we had in the prior system. Now, there's a penalty for this. At the receiver, you have to sample twice as fast because we have twice as many digital samples and they occur over the same time spacing. So we have twice the digital samples, and because the FFT algorithm is in fact twice the size, we're going to have an additional numerical complexity to be able to handle the 2 data streams. We show on the far right the constellation diagram where for a QPSK constellation where we have noisy estimates of the A and B values, which are reassigned to the bitstream segments, and that's how the system is going to work. So the idea is, will this actually work? In order to try to answer that question, we built a simulation. The simulation is a Visual Studio project in C# with a chart tool that allows us to observe the process of the processing dynamically. We use the FFTW, which is a very popular algorithm for doing FFT and IFT, and that is available using the NuGet package that is built into the Visual Studio. And we can provide you the simulation if you like. Nothing really proprietary about it. It's a fairly simple simulation. A couple of parameters of the simulation. What we're going to show is QPSK or 4QAM, so that we end up sending 2 bits per modulation cycle. We're going to use a subcarrier length of 64, so there'll be 64 separate frequencies that we modulate. We're going to use M of 128. Now, we only need to use an M of 2. M of 2 will allow us to do this quite nicely. By using an M of 128, which requires an FFT of order 8192, we end up with a much better interpolated set of data points. And we believe that makes us less sensitive to timing errors in the transmitter and the receiver. In any case, that's the value that we will use for this simulation. We've also run the simulation using a M value of 2, and we get basically similar results to what we will show here. In order to normalize the problem to allow it to be simulated easily, we're going to use a frequency spacing for the 64 subcarriers of 1 radian per second. What that gives us is a bandwidth of 64 radians per second as we multiply the frequency spacing by the number of subcarriers, which was 64. So bandwidth of 64 radians per second. What we're going to use as our carrier is 100 times the bandwidth, or 6400 radians per second. The nice thing about this setup is that it gives us a symbol time, or the time of managing, processing, transmitting, receiving one symbol. The symbol time is 1 second in this example. So let's see how this works. We see actually four panes of information here on this chart. We have these two signals, well, actually these two signals coming out of the IFFT. And these are going to be the low bandwidth signals. And what I'm showing here on the left, these panes that have the high frequency data, we're showing the first 0.1 seconds of the 1 second modulation time. Now, the red is in fact the output of the IFFT. And as you can see, the frequency content of that is quite low with respect to the remaining information. So the red is the output of the IFFT. The top pane is bitstream 1, and the bottom stream is bitstream 2. So as you can see, we get two separate sets of information using the two channels. We also show in blue is the output of the mixer, with some of the internal variables of the mixer. The blue on the top comes from here after the multiplication by the cosine of omega times t. The bottom is blue. In blue is the output of the sine omega times t. Now, the black, what is the black? The black is the same on both charts. You can see, sort of look in this particular area here, you see those peaks, you see these peaks. So the black is in fact the sum. Once we sum the two blue channels, we end up with the black channel. So let's see what this looks like. So if we say start, these are sequences of modulation cycles. And as you can see, the red behaves quite differently on each one, but on the right we see what's happening at the receiver, and we can see that we have added some noise. We can change the noise on the simulation literally in real time. If I clear it on the left, I can restart it. That shows us the behavior of the noise in terms of the estimates of the A and B. Okay, so this gives us a handle of what's happening on the transmission side with these variables. And I can also show the receiver side. So let's click on the receiver side, and here we have, let's stop this. Now what we have, let's bring back our chart. On the receiver side, the cosine omega t is the red, and on the bottom, multiplying by the sine omega t gives us the red here. We also have two other curves. One of the curve is a repeat of the output of the IFFT. So that's what we're actually trying to estimate. So the smoother curve, which is black, is the output of the IFFT at the transmitter. And the blue curve is our estimation of that curve at the receiver. And you can see that it's done with a good bit of noise that is added. The noise is 7, has a value of 7, and the peaks of the transmitted waveforms is something on the order of 25, 26, something in that order. The actual RMS amplitude of the signal is 11 if you go through the mathematics to figure that out. So the RMS of the signal is 11 and the noise is in fact 7. And let's make the noise 11 and see what happens. So we're going to clear it and we're going to restart. Now we see that at 11 we have a little bit more variability, but we're actually able to figure out the correct bins for the A and B values. So this particular design would give a pretty good bit error rate from the mathematics. So that's pretty much a result of the simulation. The bottom line is that in fact we can send two completely separate and independent bit streams across the single bandwidth of the channel. Now we also know, let's remove the noise or drop the noise. We shouldn't really have that much noise. We'll do a noise figure of 1, clear it, and as you can see now we can estimate the values much better. But let's add some of the things that we know we have to deal with. With OFDM, we have a frequency error because the receiver may have slightly different frequency knowledge as opposed to the transmitter. So we can increase the 2 parts per million. A good TCXO will give you these kind of uncertainties, so it doesn't have a dramatic impact. Although as you get a little larger, you can see that that's going to spread out. So let's leave our frequency error at around 4. As you can see, that does not have a lot of effect, quite interestingly. But now let's look at the sample timing error. We have to know the start time of the modulation sequence at the receiver, and obviously we have a start time that's at the transmitter. So let's give it a sample timing error, and the units of sample timing error here are counts of digital sampling. Remember I told you we were getting 8,192 digital samples at the receiver, and I have a 5 sample timing error. The interesting thing that you can see is we're going to have to figure out this timing error, and we're going to have to use information that's available to us at the receiver to figure out the timing error. What you can see here is that the 2 channels have different signatures in terms of timing error. So that's an interesting, and it may have value. That is, if we have 2 signatures of timing error, we will have better information to allow us to figure out exactly what that timing error is. You can see the timing error is a slip in the estimate of the output of the IFFT. Now both of them are smooth, one is simply delayed in time. So let's reduce the timing error, reduce the frequency error. Well, let's keep the frequency error. Let's drop the timing error, and let's clear it out. So now we're back to the start. Now there's another error that's very important. It's the phase. Recall we're multiplying by the carrier. So the phase of the carrier at the receiver and the phase of the carrier, we may know the carrier frequency quite accurately, but the phase can be off literally 360 degrees. So this slider allows me to change the phase error at the transmitter and the receiver. Now let's take a look at what happens. The max phase error, or the worst case phase error, is actually 45 degrees. Now you can see that the phase error actually has the exact same impact on both channels, but there are 2 times the information there to allow us to make that estimation. Let's do a 180 degree phase error. Restart it. Ah, look at that. It's not a dramatic effect. at 180 degrees, you see the values are clumped around the plus and minus 1 elements of the QPSK constellation. However, they're actually flipped. So the values are wrong, but they are indeed concentrated around the plus and minus 1. So this gives us and you can see how the two estimates are literally out of 180 degrees out of phase, which is exactly what we would expect from this. So we've actually flipped the signs on each of the AB values that are estimated. However, we can still use this as a signature for estimating the phase uncertainty. So that's what we have. We have a simulation, and the simulation has given us a pretty good indication that indeed we can pass two independent data channels across the same bandwidth, which roughly doubles the data rate.